Alright, so we're looking at section 2.2 and we're talking about quadratic functions. We've talked about the graphs of quadratic functions in the previous chapter, and we know that quadratics are going to give us parabolas. So we're going to look more specifically at the parabola. The graphs of quadratic functions are parabolas, and the quadratic functions of the form ax squared plus bx plus c, and the b and the c and the a are just going to affect where the graph shows up and how it shifts and things like that. Now, with a parabola, you have certain parts that are very important to that parabola, that define things about the parabola. The first one we're going to talk about is the vertex. The vertex is going to be the point that the parabola is going to grow from. I always treated it as the key point when I go to graph a parabola, because everything's coming from that. That's kind of that key base point that, if we were talking about just shifts, if we move that thing and grow from that in the correct direction at the correct rate, we're going to get the correct parabola. Now, as well as the vertex is actually part of the graph. It is a point on the graph. Now, some of these other things are not going to be actually parts on the graph. They're going to be properties of the graph. And one of these is called the axis of symmetry. This line is not actually part of the graph, but it is a property of that graph that is the axis of symmetry of this parabola, so that if you were to take all this side over here and fold it over, it would lay across this axis of symmetry. It's going to lay perfectly on all the points over here. Same thing over here with this one. So that's what the axis of symmetry is. It's not actually part of the graph, it's a property of the graph. So if you draw that, typically they're going to be dashed lines. I don't remember if I did this picture or if it was already done, but anyway, I would typically draw that, if I was graphing by hand, as a dashed line. I'd leave the solid lines as parts of the graph and the dashed lines as things that were just there to kind of as a reference. Alright, now with your parabola, your vertex is going to be either a minimum value if the parabola opens up, or it's going to be a maximum value if the parabola opens down. Those are key pieces of information, especially if you're looking for the range of a function, because the range of a function, if you've got a minimum, that's the lowest y value it takes, and it goes off to infinity. So for this one right here, if I was asked what the range was, if I can find the y value for the vertex and I know that parabola opens up, I know my range is going to be from 0 to infinity in this case. If I'm looking at this one and I know that parabola opens down, so I have a maximum, that y value of, what is that, 8, of 8 is the maximum value. So when I go to talk about the range of this one, it goes all the way down to negative infinity, but comes all the way up to positive 8. So once I identify that vertex of a parabola that's opening up or down, I have a maximum or a minimum, and I have its range. Now, quadratic functions are any function of the form f of x equals ax squared plus bx plus c, where a does not equal 0. You have to have an x squared term. You don't have to have a bx or a c, but you do have to have an x squared term. Otherwise, it's not a parabola. It's not a quadratic. And a, b, and c are real numbers, so no imaginary numbers here. The graph of any quadratic function is called a parabola, and parabolas are shaped like cups. Parabolas are symmetric with respect to a line called the axis of symmetry, and if a parabola is folded along its axis of symmetry, the two halves match exactly. All that stuff was stuff we just talked about, but we'll put it into words so you can actually write it all down. Alright, so graphing quadratic functions in standard form. In standard form, it's a times x minus h quantity squared plus k, where a does not equal 0. Once again, if a equals 0, the x squared would equal 0 and it would go away. This a, by the way, is exactly the same a as we were talking about in the other form as well. Now, this is in standard form. The graph of f is a parabola, and we keep hearing this over and over, whose vertex is at the point hk. Notice where h and k are right here. The parabola is symmetric with respect to the line x equals h, comes directly out of that parabola, or out of that equation. If a is greater than 0, the parabola opens up. If a is less than 0, the parabola opens down. Now, to graph a parabola, if that thing is expressed in standard form, you determine whether the function or the parabola opens upwards or downwards. Once again, depending on what a is. Determine the vertex of the parabola. You've got it right there. This number here will always change signs because of that minus right there. So whatever you're pulling out of here, change its sign. The k stays the same sign. All right, find any x-intercepts by solving f of x equals 0. The function's real zeros are the x-intercepts. So you would actually have to do some algebra there and find out when this thing here equals 0. And then you can find the y-intercept by computing f of 0. That means just go in here and plug in a 0 right there. And what's going to happen? You're going to have 0 minus some number. You're going to square that. You're going to multiply it times a, and then you're going to add k. And then plot the intercepts, the vertex, and any additional points that you may need just to make a nice, get a good idea of what the graph's going to look like, and connect these points with a smooth curve that is shaped like a cup, opening in the correct direction you found in number 1. Alright, so let's graph this using standard form. We've already got it in standard form, and as we're looking at it, we notice that here with the a, it's going to open down. We have a vertex of 3, 8. The axis of symmetry is going to be x equals whatever the x component is here. So x equals 3. To find the x-intercept, we're going to let y equal 0. So 0 equals negative 2 x minus 3 squared plus 8. Move the 8 over, divide by negative 2. You're going to get 4 is equal to x minus 3 quantity squared. Take the square root of both sides. So you end up with plus or minus the square root of 4 is equal to the square root of x minus 3 squared. Well, the square of a square root, or the square root of a square, is just itself. So you've got the plus or minus 2 over here, and when you move that 3 over, you're going to have 3 plus or minus 2, which is going to give you 5 and 1. So the y-intercept is easy. We're just going to put x in as 0. So we end up with negative 2 times 0 minus 3 squared plus 8. So the negative 3 squared is 9. 9 times negative 2 is going to give you negative 18. Negative 18 plus 8 is going to give you negative 10. So we have a y-intercept of 0, negative 10. So when we plot all those points, that's what we've got. We've got our vertex, we've got our axis of symmetry, we've got our x-intercepts, and we have our y-intercept. There's going to be typically, there's either going to be 2 of these, there's going to be 1 of these, or there's going to be 0 of those x-intercepts. At most, there's only going to be 1 y-intercept. You're never going to find more than 1 y-intercept. If you do, it's not a function. And if we were asked, what's the maximum value here? The maximum value is 8. And what do we know about where it occurs? Remember, when you're asked where a maximum occurs, they're asking for the x value. When they ask for what the maximum value is, they're looking for the y value. So the maximum occurs at 3, and the maximum is 8. All right, so let's graph the quadratic function negative parentheses x plus 2 quantity squared plus 4. So let's go through our work here. And we've got vertex is going to be at negative 2, positive 4. Because remember, whatever you're pulling out of the parentheses, you're going to change its sign because of that x minus h quantity squared. All right, and what do we also know? From that, we know the axis of symmetry is going to be x equals negative 2. So let's go ahead and plot that. We've got negative 2, negative 1, negative 2, and 4. We've got an axis of symmetry. Let me get the dashed line here. I'll do it in red. Going pretty much right down through there. Actually move that over where it's supposed to be. That'll be close enough. All right, and then what else do we need? We need the x-intercepts. So we're going to find where this is equal to 0. So we've got 0 is equal to negative x plus 2 squared plus 4. We're going to move that 4 over. So you get negative 4 equals negative x plus 2, don't forget your parentheses, squared. And remember, that's a negative 1, so I'm going to divide both sides by negative 1 and get a 4 positive over there, and x plus 2 quantity squared over here. Take the square root of both sides, so I've got plus or minus the square root of 4. Square root of x plus 2 quantity squared is going to be x plus 2. I'm going to move that over and subtract it, so I'm going to have negative 2x equals negative 2 plus or minus the square root of 4, which is 2. So that's going to give me negative 2 plus 2, which gives me 0, and negative 2 minus 2, which gives me negative 4. So those are my x-intercepts. So I'm going to have an x-intercept right there at x equals 0, and an x-intercept right there at x equals negative 4. Now, to find my y-intercept, do I really need to? Well, remember, what do we know? We're going to have, at most, one y-intercept. Well, what do I have right here? It's touching the y-intercept, or the y-axis as well. So if it touches anywhere else on that y-axis, it's not a function. Well, guess what? A parabola that opens up or down is a function. So I know I'm not going to touch the y-axis anywhere else, so I don't need to find the y-axis. I do need a point or two, though. So what I'm going to do is I'm going to go ahead and pick a value, a couple of values. I'm going to say x equals 1 and x equals negative 5. And what I'm going to do is I'm going to find the function value. So what is f of 1? Well, f of 1 is just plugging in a 1 right here. So I've got negative 1 plus 2 squared plus 4. When I simplify that, 1 plus 2 gives me 3. 3 squared gives me 9. And I've got a negative 9 plus 4, which is going to give me negative 5. So I have the point 1, negative 5. So 1, negative 1, negative 2, negative 3, negative 4, negative 5. Right there. Now, if you are thinking, we know that this point right here occurs 1, 2, 3 places over from the axis of symmetry. Well, if I go 1, 2, 3 places over from my axis of symmetry, I should have another point right there at negative 5. Now, we're going to confirm this, but remember, because of the symmetry, they should match on each side. But let's find f of negative 5 just to make sure. So when we do that, we've got negative 5 plus 2, quantity squared, plus 4. What's negative 5 plus 2? That's going to be negative 3. Negative 3 squared is going to give me a 9. That's negative 9 plus 4, which gives me negative 5 again. All right, and then all we have to do is nice and smooth sketch. It doesn't have to be pretty, just make sure it's nice and smooth. Curves. and that's good enough. From that piece of information, I know whether you know how to graph a quadratic or not. All right, I want you guys to try this one. I'm going to show you what the answer is and show you all my work, but I want you guys to pause the video, try this question, and then come back and check your work. I'm going to show you the answer in 3, 2, 1. All right, so there's the solution. You get the vertex at 3, -4, axis of symmetry at x equals 3. The x-intercepts turn out to be x equals 5 and x equals 1. So there's that one, there's that one. And the y-intercept turns out to be at y equals 5, so 0, 5. Now, once again, I wanted another point, so I went ahead and used my symmetry to figure out that I'm going to have a point right there. This is not the prettiest parabola you've ever seen or I've ever drawn by any means, but it works. I mean, that tells you pretty much all you need to know about this parabola. And the way you do symmetry is 1, 2, 3, there was this point. Well, then you just go the same height, 1, 2, 3, and there's another point over there. If this folds across this dotted red line, that point should end up with that point. So that's how I use symmetry to get an extra point if I've got an odd number of points there. Or sorry, if I've got a point that doesn't have a matching symmetric point, I can add one more. All right, graphing quadratic functions of the form f of x equals ax squared plus, that should be a plus right there. Let's go ahead and change that. Plus, fixed it. Okay, ax squared plus bx plus c. All right, now we can identify the vertex of a parabola whose equation is the form ax. First, we complete the square. Guys, do not write all this down. The key thing is down at the bottom, this is doing nothing more than proving how you're going to get to the point where you're going to know what the x coordinate of the vertex is. We're going to write that down on the next page. Don't write any of this stuff down. But if you are interested in it, that's how they actually derive what we're about to find. All right, the vertex of a parabola whose equation is f of x equals ax squared plus bx plus c. If we consider that parabola defined by the quadratic function f of x equals ax squared plus bx plus c, the parabola's vertex is, and here's where the big important formulas come in, negative b over 2a, comma, f of negative b over 2a. Now what this is this part right here. You're going to use x equals negative b over 2a to find the x component of the vertex. Once you do that, then you can take that x value, plug it back into your function, and find the y value for the vertex. So the big thing that you want to pull out right here is that x is equal to negative b over 2a. That's going to find the x component of the vertex. Let me make this a little smaller where I can write. So x component of the vertex if the equation is in this form right here. All right, now to graph that, and this is kind of hard to see, sorry about that, you're going to determine whether the parabola opens up or down by looking at A. Remember, A here is exactly the same A in standard form. So if A is positive, it opens upward. If A is negative, it opens downward. If A is 0, it's not a parabola. Then you're going to determine the vertex of the parabola using these equations right here. Find the negative b over 2a to find the x component. Then plug that x component into the original function to get the y component. And then after that, once you find the vertex, everything else is done exactly the same as it was before. You're going to find any x-intercepts by solving f of x equals 0. You're going to find the y-intercept by computing f of 0, and you're going to plot any points extra that you need according, from that. So the only thing that's really changing here is the fact that you actually have a little formula that you got to use. to find the x component for the vertex, and then you have to plug that value into the function to find the y. It's not right there in the equation. Alright, so using the form f of x equals ax squared plus bx plus c, if we've got this equation right here, we know that a is 1, b is 2, and c is 1. So we're going to find what the vertex is. So we get negative b over 2a, comma, f of negative b over 2a. We'll first of all find out what x is. So we're plugging all the parts into this right here. This is negative b over 2a. So negative b is going to be negative 2. And then we have 2 times a, and a is 1. So we end up with negative 2 over 2, which is negative 1. Then we can plug that negative 1 back in up here. That's what we're doing right here. Negative 1 squared plus 2 times negative 1 plus 1 equals 0. So we end up with this thing equaling 0. So we end up with a point, negative 1, 0, as the vertex. And then once we know that, we can just go and solve the rest of the stuff. So we have the axis of symmetry at x equals negative 1. We can solve this, set it equal to 0, and solve. So we only find that it's going to be negative 1, which, by the way, we already knew because this is a y-intercept. This verifies that it's the only one. And then our y-intercept, we plug in 0 for our x, and we end up with y being equal to 1. So we got 0, 1 is our intercept. Now, in this case, we only have 2 points that we found. But guess what? Remember, you can always use your symmetry, and we could have gotten a point right there. And you could also plug in the value of x equals 1 and find out what this was going to be, and then use symmetry to get that one. You need at least 5 points to get a good idea of what the graph's going to look like. So you may have to actually go in and say, okay, well, x equals 1, plug that into this equation here, right here. So find out what f of 1 is, and then once you find out what f of 1 is, you know that you've got a symmetric part over here that you can plot 2 points. So other than for the vertex, for any 1 point you get, you're technically getting 2 because of symmetry. Alright, so here's an example. Let's find the vertex of the function f of x equals negative x squared minus 3x plus 7. So we need to find the vertex, which means we're going to start off with finding the x component of the vertex, which is negative b over 2a. And guys, you're going to see the equation with a negative out here. You're going to see it with a negative up here. It doesn't matter as long as you only apply the negative in one place. You could even put the negative down here if you wanted to. I usually go ahead and change my b value, and then that's going to go ahead and take care of the negative, and I'm not worried about it later. So here my b is negative 3, so a negative negative 3 gives me a positive 3. And then I have 2 times negative 1. So I end up with negative 3 halves. Alright, so there's my x component, so I know what my axis of symmetry is. X equals negative 3 halves is my axis of symmetry. It's also my x component of my vertex. So I need to find out what the y component is. So I'm going to have to find f of negative 3 halves. So I have negative 3 halves squared. Sorry, I have negative 3 halves squared minus 3 times negative 3 halves plus 7. Alright, so when you square a fraction, of course, when you square anything, it's positive, so we're going to end up with the square of 3 over the square of 2. We're going to end up with 9 over 4, and then that negative is going to make it negative again. So negative 9/4 minus negative 3 times negative 3 halves is going to give me plus 9/2 plus 7. Now I need a common denominator here, and 4 is going to be it. So the first one's okay, -9/4. This one I've got to multiply top and bottom by 2. So 18/4. And then this one I've got to multiply by 4/4. That's going to be 28/4. Alright, -9 plus 18 is going to give me +9. 9 plus 28 gives me 37/4. So my vertex for this ugly thing right here is nothing more than -3/2, 37/4. Not real pretty to graph, but as far as just doing the work, it's not that big a deal. Now, the domain of any quadratic function includes all real numbers if the vertex is the graph's highest point. The range includes all the numbers at or below the y-coordinate of the vertex. If the vertex is the graph's lowest point or minimum, the range includes all real numbers at or above the y-coordinate of the vertex. We talked about that earlier. Alright, so graph the function -x² minus 3x plus 7 and use the graph to identify the domain and range. Now, we'd already graphed this, or we'd already found the key information for this. Let's go ahead and use that. We know the vertex from the previous problem is -3/2, 37/4. So -3/2 is going to be -1.5, and then I'm going at 37/4. How many times will 4 go into 37? It'll go 9 times and have 1 left over. So I'm going to go up way further than I actually have to. 6, 7, 8, 9. I'll be about right there. I'll just kind of guesstimate. And we know that since A is negative, this thing's going to open down. And you can get some points if you want to. We're not going to mess with it in this case. You could plug in 0 into that equation. You're going to get 0 minus 0 plus 7, so you're going to end up with plus 7 as your y-intercept. You can set this thing equal to 0 and solve and find your or your x-intercepts. But mostly the big thing we're looking for here is use the graph to identify the domain and range. So the domain is all reals. So -infinity to infinity. And the range is going to be from, remember, you're always doing the range from the smallest value to the largest value. What's the smallest value this thing's going to have? -infinity. And it's going to go up to and include 37/4. Now, guys, I'm going to go ahead and tell you, you're not going to have one of these that's going to have these ugly fractions that you are going to have to graph. Not fractions as ugly as that. You may have 1/2 or 1/4, but you're not going to have something like 37/4 to have to deal with on the ones I'm going to ask you to graph. But I'm not putting it outside the realm of possibility that you would need to be able to find the vertex of that even with these nasty fractions. So make sure you know how to deal with fractions. It's important. But I wouldn't make you graph one. Alright, minimum and maximum values of quadratic functions. We've already talked about this. If a is less than 0, then f has a minimum that occurs at x equals -b/2a occurs at, and this minimum is the y value. Like I said, we've talked about this, but this is where you're actually putting it down in notes. And the maximum value occurs if a is less than 0. In other words, this thing opens down, and it's going to occur at, where is the x value, what is the y value. Alright, so for the function f of x equals -3x² plus 2x minus 5, without graphing, determining whether it has a minimum or maximum, what does it have? Well, the A says it's opening down, so it's got a maximum. That was easy, wasn't it? And identify the function's domain and range. We've got to find the maximum as well. All right, so we're going to want to know what the vertex is. So the vertex, we start off with x equals negative b over 2a. We do negative 2 over 2 times negative 3. So we get negative 2 over negative 6, which is 1/3. That's where the maximum is going to occur. And we need to find out what the value is. So f of 1/3 is going to be negative 3 times 1/3 squared plus 2 times 1/3 minus 5. So 1/3 squared is 1/9 times negative 3 gives me negative 1/3. When I simplify, 2 times 1/3 is going to give me 2/3 added, and then minus 5. So negative 1/3 plus 2/3 is going to give me positive 1/3. I need to convert this to fifths. So I've got negative 1/3. I'll write all this down in one common denominator. Plus 2/3, and then minus 15/3. So negative 1 plus 2 gives me positive 1. Minus 15 gives me negative 14/3. So that is f of 1/3. So what is the maximum value? Negative 14/3. And then what's the domain and range? Well, the domain, all real numbers, always for a parabola. And the range is going to be, if this is the maximum value, we're going to go from negative infinity all the way up to negative 14/3. Now, I'll have to go back and look, but I think I made a mistake on the one before where we did domain and range. We're actually including this, so that needs to be a bracket. And I think I did parentheses on the one before, so go back and change that in your notes. The one we found before where we did domain and range, that needs to be a bracket where we've got the number, because it is actually getting up to that value because that's where the vertex is.